welcome to Cones, our monthly California Naturalist online event series. My name is Allie, and I'm the Community of Practice Educator for UC Environmental Stewards. This series is created for UC California Naturalists and UC Climate Stewards to connect across the state on topics including natural history, ecology, climate change, and the intersection of pressing human and environmental issues. We hope that this webinar series offers an opportunity for all of our alumni to continue learning about natural history and climate science and ways to get involved in action related to those things. We are expecting a very full house today, so I'm just going to go over a few bits of housekeeping. So I just want to note that this is a Zoom meeting and not a webinar. So we ask for your cooperation in making sure that you're on mute and that you turn off your video during the presentation portion of this webinar so that there are no distractions. If you're having any technical difficulties, we have several people from our team here in the meeting. So you can shoot any questions or concerns into the chat and we can work to troubleshoot those. We will have time at the end of this meeting for questions, but if you want to write any questions you have in the chat, please just write question at the start of your question, and that will help us to collate them and find them and answer them at the end. And this presentation is being recorded. It'll take me a couple days just to clean up the closed captioning and post it to YouTube, but I will share a link to our past Cones events in the chat momentarily so that you guys can all check those out as well. And I would like to start off by acknowledging that this virtual presentation is taking place throughout the unceded territory of California, home to nearly 200 tribal nations. I'm speaking to you from Nevada City, which is Nisenan land. We acknowledge and honor the original inhabitants of our various regions, and we encourage everyone to learn which tribal nations are indigenous to the areas where you are now living. You can use these links on the slide to help find who's in what lands you're currently residing on. And now I'm going to stop my share and just do a brief introduction of our presenter today. Whoop. Let me get to the right. So we are so lucky today to have Dr. Daniel Swain with us. Daniel is a climate scientist focused on the dynamics and impacts of extreme events, including droughts, floods, storms, and wildfires on a warming planet. Daniel holds joint appointment as a climate scientist at the University of California Agriculture and Natural Resources and as a research partner at the NSF National Center for Atmospheric Research. He engages extensively with journalists and other media partners, serving as a climate and weather science liaison to print, television, radio, and web-based outlets to facilitate accessible and accurate coverage and conversation surrounding climate change. Daniel is an alumnus of the University of California, Davis, with a BS in atmospheric scientist, and of Stanford University, where he has a PhD in Earth System Science, and completed his postdoctoral work at UCLA. He also authors the widely read Weather West blog, which you can find at weatherwest.com, which provides real-time perspectives on California weather and climate and can be found on Twitter at weather_west, Blue Sky at weatherwest, and most importantly, where he's hosting a lot of his conversations is on YouTube at Weather West. And we'll add that link to the chat right now. But for right now, I'm going to turn it over to Daniel and let him start his presentation. Thanks so much again, Daniel.
Well, thanks for having me. It's always great to join these UC and ANR programs, and also thank you for a very well organized lunchtime event. Sometimes these virtual meetings are a little bit chaotic, but this one is really nice and smooth so far, so I'll try and keep it that way. So what I'm going to do is share my screen, so you'll briefly see all my whole desktop, and then you'll see my slides, hopefully just a second or two thereafter, full screen, and then I will get going. All right, I think we're there. So without further ado, what I really wanted to talk about today, and clearly based on the number of folks who've joined, I think there's a lot of interest in this moment, is climate change in California, but not just what we know about climate change affirmatively, but also what we don't know, which can be equally important and which often holds some surprises based on recent experience in describing the unknowns, and also some recent lessons learned. There have been some pretty tumultuous events in California and the weather, climate, and wildfire world in recent years. What have we learned from those in terms of what might be ahead? So just a brief primer here on climate change that may be a little old hat to a number of folks who are here, but just bear with me. I've updated these numbers up through this year, so those may be new to you. But the Earth, of course, is warming, causing changes in the Earth's climate beyond just temperatures. So even though we talk about global warming in terms of how much the Earth's average temperature has increased or will increase or may increase, the main reason we care about it is actually everything other than the Earth's mean temperature. So that number is a useful heuristic or indicator, but in itself, it isn't so much the problem, it's everything else that comes with those rising temperatures. And this warming that we've observed over the past century and a half or so is caused almost exclusively by the increased accumulation of heat-trapping greenhouse gases in the atmosphere, mainly themselves generated through human activities. Uh, and a lot of that comes from the burning of fossil fuels, but also the way we've changed the way we use and manage the land, both of which have resulted either in direct or indirect emissions of those heat-trapping greenhouse gases. As of right now, on the way that the IPCC, or Intergovernmental Panel on Climate Change, the entity responsible for those recurring climate change reports you hear about, if you use their methodology, which is sort of on a multi-decadal average basis, the Earth is warmed by about 1.3 degrees centigrade so far, or about 2.5 degrees Fahrenheit. But you may have heard in the news recently, oh, well, this year was the first year above 1.5. And that is true. 2023 and 2024 were considerably warmer even than that, but we haven't reached that 1.5 degrees yet on a sustained multi-year basis. But the last couple of years truly have been that warm. And at this point, although there's a lot of uncertainty in terms of what we humans will do in the coming decades, we're still on a path for about 2.7 to 3 degrees centigrade of global warming by the end of the current century, which means that on our current path, we're likely to double the amount of warming still, even with the changes that we've made to our energy production systems, the way we live our lives so far. We're still on track to about double the amount of warming we've seen to date. And it probably shouldn't be too much of a surprise then that California, like the rest of the world, is a warmer place than it used to be. We've seen strong warming trend throughout California. The note about the Bay Area, the slide is from a talk oriented toward Bay Area folks, but of course the number varies depending on which part of California you're in, but the general trend looks rather similar. And there's also a commonality that there has generally been faster warming at inland portions of California as opposed to the coast and at higher elevations. And this is not just a statement that the inland valleys are generally hotter than the coast. That's, of course, true. Just think of a recent summer heat wave where it's foggy in San Francisco and hot in Sacramento. But this is actually a statement that that gap, that difference, that differential between the coast and inland areas is itself accentuating further. So there already was a substantial gradient between the cool coast, warm inland, especially in summer. We're seeing that to an even greater degree now than we used to. And in the post-2010 era, we have seen this sort of step change towards more sustained warmth. And this is true not just as is shown here for Sonoma County, but generally throughout most of California. there was a sudden elevation around 2010 of temperatures that has leveled off a little bit in the last few years, but we've not gone back down to baseline. We're sort of living in this climate changed world where the post 2010 era looks very different than all of the years in our historical record going back to the late 1800s before it. And if you look, and this plot here is for California in general for summer, June through August, summer heat waves have clearly gotten hotter, longer, and more intense, especially since the early 1980s. And in recent summers, in fact, last summer was the singularly hottest summer on record, although similar to what we experienced in 2021, which was then also the warmest summer on record. Before it, I believe, 2017, the warmest summer on record, preceded by 2015. So you get the picture. There's a lot of record warm summers in recent years. It may not have felt like it this year or last year if you're in San Francisco or along the immediate coast, but inland, it's been a very different story. In fact, all of California's top 3 hottest summers on record have occurred in the past decade. Which is kind of a remarkable statistic because in a stable climate that would be almost impossible. But there is also something interesting going on, as I mentioned, where the coast in California summer is doing something a little bit different than California's inland areas. And I think this is pretty apparent if you look at summer temperatures, for example, on the top panel here, that's the average summer temperature on a statewide basis. You see the clear warming trend that has accelerated since the 1980s with the recent years of record warmth. But if you look at San Francisco County, of course, a coastal county that's infamous for its summer fog, we actually see a little bit of a different picture. Still a summer warming trend, still all of the hottest summers on record occurring in the last decade, but it's a much more muted warming trend since the 1970s. In fact, San Francisco County, for example, has been warming 4 times more slowly than the rest of the state. Now, you could say the rest of the state is warming 4 times faster than San Francisco. It would be equally true. But it is notable that the already hot places are getting hotter faster and that the cooler places, they're still getting warmer, but at a much slower pace than the hotter inland areas. And also that the last couple of summers have been less extremely warm than inland areas have experienced in those recent years. That's partly because this coastal fog is still making a really strong showing in a lot of summers. And that is an interesting observation because the future of fog, coastal fog in summer in California, is still surprisingly uncertain. You could even call it foggy if you wanted to entertain a very obvious pun. But the reason for this is kind of interesting because a lot of folks will often say, well, it's getting warmer and the air mass is getting drier, so shouldn't there be less fog? Well, that's one important factor, but it's only one of 2. And the other one is actually potentially going to act in the opposite direction. We do see warming temperatures, of course, and we do see drier summer heat wave air masses inland. And the air above this relatively shallow coastal marine layer is also getting drier. But the part of the reason we have morning low clouds and fog in California in spring and early summer is that we have this temperature differential, cool coast, warm inland, because we have this really cool ocean, especially off the coast of the San Francisco Bay Area and the North Coast with the cold California current. That cold water upwelling from beneath near the Farallon Islands, for example, that water is some of the coldest water on Earth at that latitude, believe it or not. So that water offshore stays really cool, that there's plenty of cool ocean water in the deep ocean that's available even in a warming world to continue to offer that coastal cooling. But that marine layer is the circulation, the wind pattern that blows that coastal fog inland some days is driven precisely by that pressure differential that's set up by that temperature contrast. So the hot Sacramento Valley, the cool ocean beach coastline, that differential is itself what drives the sea breeze that draws that cool marine air inland during those warm summer days. And so the hotter it gets inland, the stronger that circulation becomes, the more the Central Valley wants to cause to generate that inland flow of cool marine air. So you have these two competing factors, the warming, drying air mass at scale, but this local effect where the hotter it gets inland, the more aggressively the inland areas try and pull that cool marine air into the Central Valley. So that's the tug of war, and honestly, we don't really know which side is going to win. And I think we've seen that in recent years in this very rapid increase in temperatures across California's inland areas, but much weaker trends closer to the coast. Will it continue? Will one of these factors start to win out over the other is an interesting question that, despite much discussion, I don't think we have a good answer to. So surprisingly, something as seemingly mundane as California's fog and rain layer is one of the big unknowns of our future climate. Something that seems more complicated, though, and is actually less of an unknown, is what we may see when it comes to increasing hydroclimate extremes. In other words, increasingly wide swings between extremely dry and extremely wet conditions and associated drought, wildfire, and flood risk. This slide is going to look technical, but I assure you that I'll get to the point pretty quickly. The main point here, if you think back to whatever level of mathematical knowledge that you have from your life, is that there's an important equation in meteorology and climate science. Excuse me, it's known as the Clausius-Clapeyron relation. And essentially what it tells us is that the capacity of the air to hold water vapor increases exponentially for a linear increase in temperature. So in other words, the water vapor holding capacity of air rises by about 3 or 4% per degree Fahrenheit of warming. Think of it like compound interest. If you're unlucky, compound interest on a mortgage or a credit card balance. If you're lucky, compound interest, I don't know, in a savings account or something, or a CD in a bank. But the idea is that for every 3 or 4% increment, for every degree increment of warming, the increment by which the atmosphere's capacity to hold water vapor increases slightly more than the last. So the first 3 or 4% is smaller than the next 3 or 4%. It's compounding. What this means is that global warming then brings about a nonlinear, literally exponential in this case, increase in the water vapor holding capacity of air. And really what you can think of as a shortcut is that warmer air equals thirstier air. This is actually,
Daniel, do you mind if I interrupt for just a second? Would
sure.
you just press OK on the meeting being transcribed so that it, because that's sharing on our screen as well.
Oh, okay. Yes, there we
Thank
go.
you.
Okay. Is that the only thing that's sharing on screen?
Now it's just your slides again. Yeah.
Okay. All right. Thank you. So interestingly, the science behind this goes all the way back to the mid-1800s, long before we had computational climate models, and this was actually something that was originally demonstrated with really basic laboratory experiments. But what's so fascinating is that despite having been understood for the better part of 2 centuries at this point, it also is emergent both in observations and in these complex numerical climate models that we use to project future climate. So it's one of those things that is both very complicated and also extremely well understood, in which we have very high confidence that this is driving a lot of the changes we see before us. And one of the most practical implications of this is something that I like to call the expanding atmospheric sponge effect. You can visualize the tangible effects of the Clausius-Clapeyron relation in the form of just thinking about the atmosphere in a warming world looking like a progressively larger kitchen sponge, literally just an ordinary kitchen sponge. As temperatures rise, the ambient air becomes, if you will, spongier. Imagine a progressively larger kitchen sponge that's initially dry. So your ordinary sponge and your perhaps comically oversized one, they both have they're both dry initially, right? When you buy them at the store and have zero water in them. So even though the larger sponge has the capacity to potentially absorb more water, unless there is water available to absorb, it does not actually contain more water. But if you spill a bunch of water on your kitchen counter and you use the small or the larger one to soak it up, in that case, the larger one is actually going to contain more water. And that's why this analogy works so well, because it explains both the dry and the wet side of the implications. On the dry side, the larger sponge is essentially trying to extract more and more water out of the landscape, out of plants via transpiration, out of the land surface via evaporation, out of bodies of water, leading to worse droughts and potentially worse wildfires as vegetation dries out. But on the other hand, when there is water available to evaporate, and when you try and wring it out over the sink, it's going to yield more water, the larger sponge will. That's analogous to the increased potential for extreme precipitation when conditions are favorable. So what this really means in practice, all of this comes down to science from the mid-1800s, the Clausius-Clapeyron effect visualized using the analogy of the expanding atmospheric sponge. But the basic implications are this: much heavier downpours when conditions are conducive to rain, but also greater atmospheric thirst and increasing risk of drought and wildfire the rest of the time. You could also call that increasing hydroclimate whiplash, these wide swings between wet and dry. So California climate, since I don't think this probably requires too much of an introduction, since this is a California audience, you all know that it's wet in the winter, dry in the summer, unless you happen to be on the eastern slopes of the Sierra or in the southeastern deserts, and then you have a summer monsoonal pattern with afternoon summer thunderstorms like we're seeing this week, finally. But in general, you have this seasonal cycle where almost all of California's precipitation falls in the cool season, and very little of it, except in the deserts where it's fairly dry, falls in the summer. We also have this, so we have this strongly seasonal cycle. We also have a strong cycle, a strong latitudinal gradient. So obviously it's wetter in Northern California than Southern California. Obviously you can find wet pockets in Southern California in the mountains and dry pockets in the deeper valleys of Northern California, but generally it's wet in the north and dry in the south. We also have a lot of year-to-year variability in precipitation. We have a lot of years where precipitation is way below the average, and also a lot of years where it's way above the average. That may sound obvious because, of course, an average is just that, a statistical construct of all of the years above and below average over time. But if you actually look at the map on the right here, the values aren't super important, but the main point is that this is essentially a map showing how much does precipitation vary from year to year at different points in the US, and the greens and blues are the highest values. It's very clear that California, and in particular Central and Southern California, have by far the largest year-to-year variation in annual precipitation of anywhere in the continental US. In fact, it's one of the highest coefficients of variation for almost any place in the world, because it is not an extremely arid environment, but we have some individual years that are more characteristic of a highly arid desert, but then we have other years that are exceptionally wet. And the reason for this is that we kind of live on the boundary between more active subtropical weather conditions, more stable subtropical weather regime to our south, and a more unstable active weather regime in the mid-latitude influence to the north. So what do we see so far in terms of climate trends in California? Well, I've already talked about temperature. It's getting warmer. It's a complicated picture, but the basic story about temperature is pretty simple. It's getting warm out there. But interestingly, when you look at annual average precipitation in California, there really hasn't been much of a trend in the last century. But we do see an increase in the moisture variability over that same period, interestingly. So no trend in average precipitation, but an increase in its variability. And we also see an increase, pretty strong increase actually, towards more frequent and more severe droughts. But again, keep in mind, this is occurring in a place that has not seen a large or sustained decrease in annual average precipitation. So what the heck is going on here? Well, this is precisely sort of what I was talking about earlier, where the expanding atmospheric sponge does not necessarily tell us about what happens on average with precipitation, but it tells us what happens with the extremes of precipitation and evaporation. And if there's relatively little change in average precipitation, that could be for two reasons. One could be if there truly is nothing changing in the hydroclimate system, then the average will stay the same. That's pretty obvious. But the other thing that could be happening is that we could be seeing an increase in extremely wet events and also an increase in extremely dry events in proportions that partially or largely cancel each other out mathematically. They don't in terms of societal and ecosystem impacts, but that in turn, that as it turns out, is exactly what's going on, is that we're seeing this balancing where little mean trend and average precipitation hides the fact that we are seeing this acceleration in the hydrologic cycle on both the wet and the dry side of things. So just for a few examples of why this matters, why do we care about this? I've had some version of this slide I've started creating in 2016 or 2017. And I have added a new slide every couple of years because we keep getting more and more examples. So for those in Southern California or the Central Coast, you probably remember the Thomas Fire in December 2017. It was a devastating fire. It burned hundreds of homes. It became the largest fire in state modern history in December, since been eclipsed multiple times since then, but then was followed by a catastrophic debris flow in Montecito in Santa Barbara County just a few weeks later. If you characterize this period using the climatological average over the 2 months, it was mostly sunny and breezy with below average precipitation, which I think is very clear just from the images here. This is a great example of how if we only consider the average values, then we're essentially missing the point. We're going to miss a lot of what we care about. And there's just a lot of other examples of this. These are all parts of California, by the way. I'm just going to scroll through these relatively quickly, that have seen little or no change in annual average precipitation over this period. And just think about, though, the images you're seeing on screen and how little mean change is largely irrelevant in understanding the extremes at both ends of the distribution. That was Butte County up with Oroville Reservoir, but we go to Sonoma County and we just look at the sequence of events we've seen. Again, is an extraordinary alternation. This is just a decade. I'm only using a 10-year period here, and I'm going to different parts of California, and the sequencing has been rather incredible here. And we just keep going. Now to Southern California, now San Bernardino County. Again, similar sorts of extremes that we've seen in recent years. And we could even update some of these with stuff that's happened in 2025. And speaking of which, I did want to go and use the really devastating example that we've seen this year in Southern California. A really dramatic example specifically of how the consequences of hydroclimate whiplash, these rather sudden changes between wet and dry conditions, can have impacts that are greater than, if you will, they're greater than the sum of their parts. And in this case, I think this will become obvious when we think about the sequence of events that occurred leading up to the January 2025 wildfires, which have now become the costliest in California history. We actually had a couple of really wet years in Southern California. In fact, in April of 2024, so a little over a year ago, conditions in Southern California were extraordinarily wet, much wetter than usual. In fact, some parts of Los Angeles County where the fires burned had their wettest 18-month period on record, ending in spring 2024. That led to abundant accumulation of herbaceous vegetation. So the grasses, the forbs, and a lot of the shrubs that characterize the coastal plain and the lower mountain and foothill regions of Southern California that went on to burn these fires. In fact, biomass, literally the amount of plant matter that grew by the summer of 2024 was double the average amount. So literally twice as much potential fuel for fires to come as a result of these really wet conditions. But we then had across California's inland regions a sustained summer of record heat and evaporative demand, not at the coast. Southern California coastal LA County, June through August last year, not super hot, but then September came along and we had a record-breaking heat wave, record-breaking evaporative demand, and then there was a failure of the rainy season to begin. It did not rain at all in Southern California in September or October or November or December, and then we got to January and it still hadn't rained, and we got this extreme offshore wind event. So it was the catalyst for these wind-driven catastrophic fires in the urban interface. So the reason why this matters is this 1-2-3 punch. The extremely wet conditions, more fuel for the fires to come. The extremely hot and extremely dry conditions desiccated that fuel to record-breaking levels of dryness. So now we have a record-breaking amount of fuel that is record-breakingly dry, facilitated by this transition from very wet to very dry. Some form of this would have happened either way, but the particular sequence from extremely wet to record dry was one of the main things that set the stage here. And then, of course, the third punch were those extremely critical fire weather conditions when those hurricane force downslope winds, literally hurricane force, created this firestorm conditions once these highly abundant and record dry vegetation ignited, with consequences that were obviously quite severe. Just for some further context here, we did a very rapid analysis that was published earlier this year, just in the wake of these events, and we found that in coastal Southern California, so in precisely the part of the state that was most relevant for this event, that the variability of landscape level moisture conditions has increased by about 25%, if for the 6-month period ending in December, which is relevant for these fires. That's a pretty significant increase at the same time that the overall level of dryness on average has increased. So the variability of moisture has increased just as the dryness has as well. We also found that the maximum magnitude of extreme fire weather conditions during peak Santa Ana wind season, which is usually winter, November through January, so the winds occurring as they did in January was not in itself unusual. They were particularly strong, but that was exactly when you would expect to see them. But the magnitude of those fire weather conditions in winter in Southern California have actually increased by quite a lot, by around 36% since the 1980s. That is not a small increase, and it means that the likelihood that we see extreme fire weather days during Santa Ana wind season has greatly increased. There's always anecdotes about, yes, there were some winter fires in Southern California even decades ago, probably centuries ago, and that's true. But we're now seeing a lot of days in the winter in Southern California where these conditions are rather extreme, whereas they used to be essentially uncommon or even rare. So when it comes to precipitation in California, we can expect potentially a wetter and drier future, which I think hopefully by this point in the talk, it's becoming a little bit clearer what I mean by that. We should also expect to see seasonally a further amplification of our already short and sharp seasonal cycle. So in most of California, of course, it's wet in the winter, dry in the summer, with some shoulder seasons transitioning in between. Autumn and spring, they can be dry some years, wet some years, but in general, they're transition seasons. We do expect both autumn and spring will probably become drier on average. So a longer, hotter, dry season. But interestingly, the peak winter months could potentially get a bit wetter. So an even more strongly, more extremely seasonal cycle than we're used to. And we're already used to one of the most accentuated seasonal cycles in all of North America. This has pretty major implications, of course, for things like wildfire risk and agriculture, let alone natural ecosystems, because it means that the irrigation season or the precipitation moisture deficit season in natural lands and ecosystems and open spaces will be longer. It will also be hotter and drier during the longer dry season, but it also means that the wet season, when it comes, could come as a bit of a sudden shock and could potentially bring a greater risk of floods. And I think this is driven home a little bit. This is an older chart, but honestly, the overall picture hasn't changed very much. We don't really have much sign of a large increase or decrease in annual average precipitation. In fact, we're actually less confident, believe it or not, in 2025 regarding how California's annual average precipitation will change than we were a decade ago, which is for reasons that are interesting to talk about, but are beyond the scope of today's talk. But the main point here is that even in the very same climate predictive models that tell us that we don't really know much about how California's annual average precipitation may change, are very confident that the variability of winter precipitation will greatly increase everywhere in California. Deserts, mountains, north versus south, doesn't matter. Expect more variability from year to year and within seasons. So more really dry and really wet months, even within a single given year. And I'll move through this a little bit quickly, but this does get into some of the reasons why we have some uncertainties regarding what might be coming next. And the long story made short is essentially this: most climate models, and actually there's a typo here. I just created the slide. Most climate models suggest an El Nino-like trend in Pacific Ocean conditions with climate change. In other words, more rapid warming of the eastern tropical Pacific as opposed to the western tropical Pacific, bringing about El Nino-like long-term trends. But in the real world, what we've actually seen and I have this reversed here, so I need to change this slide. So apologies, but what we've actually seen is a La Nina-like trend. So the climate models say, okay, the ocean's going to look more like El Nino semi-permanently, but the real world has actually looked more like La Nina. So essentially the opposite, with relatively cool conditions in the eastern tropical Pacific Ocean. There's brand new work suggesting that, in fact, there's a pretty good reason why this might have occurred, and it might be yet another human fingerprint of climate change that we have underestimated. So the too long didn't read version of this, if you will, is that major uncertainties exist with what the heck is going to happen with El Nino and La Nina and the Pacific Decadal Oscillation, and these could have pretty large implications for California and the Southwest. This explains why we don't know what's going to happen on average with California precipitation. But what I will say is this: we're very confident in the expanding atmospheric sponge. So regardless of what happens with the annual average precipitation, that expanding atmospheric sponge is going to drive drier dries and wetter wets superimposed on top of whatever happens to El Nino and the PDO. So on the wet side of things, I know I've talked more about dry. Atmospheric river storms, you may have heard of them, are the main moisture delivery mechanism in California. Historically, they will continue to be so even in a much warmer future. And they're getting moister, or they will be getting moister pretty soon in a warming world. And in particular, it's the most extreme atmospheric rivers that will become moister faster than the rest of them. In fact, we actually think that the weaker atmospheric rivers may occur less frequently or become even weaker, but the strongest will become stronger. You might sense a theme here, this increased accentuation across the distribution of events. We do know that California is susceptible to mega flood risk in a way that is not always obvious for folks who have lived in an era of modern water infrastructure that's protected much of the state from that risk over the past century or so. We do know that great floods in this part of the world happen every 1 to 200 years. The last really big one was probably in 1862, known as uh, the Great Flood of 1862, somewhat uncreatively. Uh, but it's pretty clear that a modern day repeat, even with our modern water infrastructure, would be disastrous for contemporary California, and that there is a substantial risk, potentially greater than 50-50 risk, of something similar recurring in the next 40 years or so. And we went on to do additional research into this a couple of years back that suggests that while we've been so worried about heat waves and droughts in recent years and wildfires, understandably so, we've seen some terrible ones, that the risk of a California mega flood has quietly doubled in the background. How can that happen in an era where we've seen so much heat and dryness and wildfire? Well, again, blame the expanding atmospheric sponge. The very same physical and thermodynamic mechanisms that have driven more obvious manifestation of climate change in California in recent years, these droughts and these wildfires, is also quietly in the background, waiting for an opportunity to be wrung out. So I've already talked about how droughts, worsening droughts, not just in California, but in the Southwest in general, uh, are amplifying in a warming climate. And this plot's on the left here, again, it's a recurring familiar theme, but now this is for the lower Colorado Basin. So for all of the lower and upper Colorado Basins, excuse me. So all of the states that have watersheds on the Colorado River that drain into the Colorado River. And so you can kind of see how this picture is not just California specific, but indeed in the Southwest, there's been some decrease in precipitation, not huge, but an enormous increase in temperature and in drought frequency and severity. So once again, what we see is that a long-term trend towards worsening and more frequent drought in this part of the country is due to the increasing evaporative demand uh, uh, thanks to the expanding atmospheric sponge. And this is essentially viewed in another way. Droughts in this part of the country, in this part of the world, used to be cold or hot. In the 60s, 70s, 80s, you could get a drought, low precipitation, where temperatures were below average. But you can't anymore because temperatures are always above average. So now all droughts are hot droughts, and now all droughts are amplified by warm temperature anomalies rather than randomly amplified or mitigated, respectively, by hot or cool. And this is really what's going on when it comes to the expanding wildfire situation in the U.S. West. Essentially, there is an exponential relationship between vegetation dryness and the extent and severity of fires, especially in forested ecosystems. And we see this in real world data. It's an alarming curve, and the challenge is that the increase in the vegetation dryness driven by this expanding atmospheric sponge is itself exponential. So whenever we start seeing exponential processes, nonlinear processes, it always gives us a little bit of pause, because in our minds, we're often used to thinking linearly in terms of how systems interact with each other. Uh, but this is one of the reasons why it feels like the wildfire situation in the US West has accelerated, because it literally has, as the aridity itself has accelerated. And this is something that I believe former California Governor Jerry Brown coined, this notion of a new abnormal for California. I'm not sure if it was specifically in the context of wildfire, but I think it's appropriate here because I actually dislike the term new normal. And I think the reason for that is apparent by just looking at this map plot of the number of days with extreme fire weather indices in autumn projected moving forward at different levels of global warming. You can see where we are now in this right smack dab in the middle of the quote unquote current period from 2006 to 2035, which is already a redder and more orange map, denoting more extreme fire weather days than we were a few decades ago. But look how much further increase there is at 1.5 to 3 degrees centigrade of global warming, a place we're likely headed. That's a very different map still than where we are today. And so this notion that we should get used to what we currently experience as a new normal, I think, is flawed, because the current normal is really just a temporary way station on a path towards further change. So yes, the present is definitely different than the past, but don't get too used to it, because we're still on this roller coaster. And I think just these visual examples, I've unfortunately been adding images to this panel year on year for a number of years now. But I do want to offer a message. Hopefully, it's a little bit more constructive than some of the doomy and gloomy picture that may be coming through right now, which is that wildfire itself is not inherently bad. It's a natural process. In many places, it's something that has actually been lacking on the landscape in recent decades over the past century or so. But it's the intersection between wildfire and populated areas that has become a real crisis. And we may not have seen the worst of things, and still worse disasters are plausible, unfortunately, is a line that I've had in the slide originally after the Tubbs fire, which then ended up being true in the Camp Fire, and then was arguably then true again in the Eaton and Palisades fire just this year. So unfortunately, I think this is empirically true, but I think this is really what I want to emphasize here, is that the burning question is, will we do the necessary work to decouple wildfire from catastrophe? Because they're not inherently linked. They don't have to be. And a lot of what we need to do in this space, obviously climate change is a major driver, but it's not the only thing that's going on. In fact, I think about a lot of what we can do is addressing things at a more local and a more short-term basis than climate change itself. So just to sum it all up, what can we expect in a warming California? Well, the physical reality, as I've been really talking about today, it's obviously warmer, but we also should expect an increase in both precipitation intensity and in overall aridity. I didn't talk so much about it today, but in the mountains, as you might expect, a pretty dramatic loss of snowpack. We've already seen that trend begin, and also more extreme heat and more intense runoff. And I think if you take one thing away from this talk, it's that expect ever greater variability when it comes to hydroclimate in a warming world. So think hydroclimate whiplash. Don't think drying or wetting trends. Think more wet and more dry at different times, but sometimes in the same place at different points in time, and occasionally even in the same year. The driest dries will become still drier, but so too will the wettest wets, and that could be a blessing or a curse, depending on the context and preparedness. The good news is that it does not appear that California is going to shrivel up like a raisin. We will still see wet years. We will still get big inflows into those reservoirs in the Sierra Nevada that are so critical. We will still get wetter periods that help our forests and our landscapes recover from the droughts. We just are coming out of one of those periods, I think, right now. But that also makes our water harder to manage. It makes those reservoirs less effective at doing their job of flood protection and water storage. It makes landscapes have to deal with ever greater extremes and the people who interact with them as well. And so, in that vein, I think it's becoming increasingly clear that being flexible and being proactive with our water and climate interventions are going to be key. Not saying what do we do to increase our resilience to drought, or what do we do to increase our resilience to flood, or what do we do singularly to increase our resilience to fire, but thinking about all of these things in the same breath, in the same approach, and thinking about which kinds of interventions are potentially ones that can help us with multiple or all of the above in the same intervention, because there are some where you might increase your resilience to drought at the expense of your resilience to flood. And that would be something that would be a mistake. So thinking about how we can co-manage these risks is really going to be critical. And so I think I covered a lot of this. I'm going to skip through this slide for the benefit of having some time for questions. But just to close quickly, climate change is here. It's no longer a prediction regarding the future, but it's on our doorstep, and it's coming in the front door. In most ways, the climate of California will be familiar. In some ways, a more extreme version of what we were used to, but there will be major societal and ecosystem consequences from that accentuation. I already covered the increasing whiplash, but we will see more severe floods in addition to more severe droughts and wildfires, and we ignore flood risk at our peril. There's been more focus on drought and wildfire in recent years. I think it's high time to expand that focus to include flood as well. And we do know a lot about a lot of this, but there are still some significant uncertainties, especially when it comes to something like El Nino, for example. It's a pretty big wild card, and right now we don't know exactly how it's going to play out. There's also some perhaps less consequential, but still interesting ones, like what's going to happen to the coastal fauna. All right, so I will leave it at that. If you're interested in engaging on various media platforms, social media, there's a bunch of options up on your screen right now, and I do want to leave as much time as possible for questions. So thank you for joining today.
Wonderful. Thank you so much, Daniel. Before we get into questions, I'm just going to launch a quick question poll. And this just helps us to track everything about how these various presentations are going. So you should have seen the poll pop up on your screen. And if you could just quickly answer these 4 questions, they're all on a scale of strongly agree to strongly disagree. And we just use this data to help with preparing our future cones. As this poll gets started, definitely a huge part of our climate stewards course is in climate communication. And we use analogies a lot in helping to train our participants in climate communication. And so one person just asked if you could go over the expanding sponge analogy so that they can help in communicating that concept to people they speak to about climate change.
Yeah, definitely. And I'll bring that slide back up just for the visual. I don't know why PowerPoint needs that, but anyway, I'll go back to that slide just to keep the visual as an aid, since visual aids are always so important in communicating and when using analogies. Okay, so here's essentially and I'm going to move this poll off to the left so it's still up there. Actually, move it off screen. Well, I just made it big.
It's okay. It looks like we have enough answers. I'm going to actually end the poll and download the results. So that'll be off everyone's screen.
Okay, sounds good. Just didn't want to close out of it prematurely. So, the basic idea here is that air has some intrinsic capacity to hold, if you will, water vapor that is dependent, for all intents and purposes, only on temperature. So if you only know one thing about the ambient air, and that thing is how warm it is, you can say with pretty high accuracy what the maximum amount of water vapor that could be in that air is. This is actually the basis for how we calculate relative humidity, by the way, because relative humidity is a measure of how much moisture is in the air relative to how much moisture could be in the air. And the reason, and the could be in the air part is itself a function of temperature. So if you have, for example, 30% relative humidity, and it's a cold winter day. Imagine you're, in the mountains. It's clear, crisp, and cold. It's 20 degrees Fahrenheit, and the relative humidity is 30%. It's actually really dry air. There's extremely little moisture in that 20-degree Fahrenheit air at 30% relative humidity. But instead, imagine you're down in the Imperial Valley, down in Brawley or something, in a well-irrigated agricultural field, and it's July and the monsoon is present, and it's 112 degrees Fahrenheit, and that humidity is 30%. Believe it or not, that summer air in Brawley has far more moisture in it in absolute terms. If you were to actually squeeze that moisture out of the air and actually measure it on a scale, the actual weight of the water vapor, 30% relative humidity in that very hot air is a lot more absolute water than 30% relative humidity with that cold winter air in that example. So that's one way of thinking about how this works. It really just means that as the air warms at a given level of saturation, at a given relative humidity, there's more and more actual water in that air at those warmer temperatures. Now, that was just an example of a seasonal variation, right? We're talking about winter in the mountains versus summer in the Imperial Valley. That's a normal variation. This is not just a climate change thing, though. It describes partly why we have the climate variations that we do from season to season and from place to place. But the basic idea behind the sponge is this. The air isn't always at 100% relative humidity, right? If it were, we would constantly be living in fog. And if you're in San Francisco, on the coast side of San Francisco, maybe it feels like, at least this year, we're constantly living in fog because, in fact, the relative humidity has been near 100% for a lot of the summer, and you have been in a cloud in that fog a lot of the time. But if you're anywhere else where the humidity isn't 100%, you're not constantly experiencing that maximum saturation of the expanding sponge. And it becomes most relevant during a storm when there is precipitation and clouds and 100% relative humidity. In those cases, you're actually realizing the latent moisture potential of the air. And so when it's raining, you can, another expression that works is when it rains, it pours, or to extend it to climate change, when it rains increasingly, it pours for the same reason. It doesn't rain more all the time. It doesn't mean there's more moisture in the air always, but it means the ceiling on how much moisture could be in the air if it's fully saturated is rising rapidly. So this expanding atmospheric sponge analogy, I've actually used both an ordinary and comically oversized sponge, like the ones on the screen right now, on camera to demonstrate this. You can actually demonstrate this with real live kitchen sponges and just some water. The analogy works so well because the unsaturated sponge is like akin to the atmosphere most of the time in California when it's not foggy or cloudy and raining. And the saturated one applies when you actually do have a winter storm or precipitation event, when you can wring out all of that additional moisture. So I don't know, hopefully that got to the question. I don't want to spend too much more time on it, but hopefully that was helpful.
Yeah, and I'm just going to power through a few, and I'm sorry if I don't get to everyone's questions. So the next question is about the fog variability and if we've seen a measurable and about how fog changes might be impacting redwood growth. Like, have we seen changes in that might impact that? And just kind of rephrasing what you said about if we know if the fog will continue, or a little bit about that tension that you had mentioned.
Yeah, I mean, we do know that there obviously are some major coastal ecosystems in California that are dependent on fog drip. So think, the redwoods in many places. Uh, actually get quite a lot of essentially precipitation, self-induced precipitation in some cases from fog drip, literally where the fog will condense on the trees themselves and literally drip down to the forest floor and then keep the soil moist, which allows the trees to access that moisture through their roots. So it's a really important form of moisture delivery in these ecosystems. It's good that we haven't seen more decrease in that fog drip. So we haven't in the long run. And there's one study that claims that we did, but the study ended in the early, essentially the mid 2000s, and things have looked very different since 2005. We've actually seen a return of more fog and more coastal fog drip, even in this period of increasing drought and wildfire and temperature overall. So I think we don't really know yet, and I think that I've seen a number of media articles that have pointed to this single study that is actually very different from how things have looked in the last 15 or 20 years. 2005 was a long time ago now. It's hard to believe. Uh, but I think this is just an example too of why it's so important to keep up to date with, how the science has evolved, with how the real world has evolved, and whether or not they've evolved in the same direction as anticipated. And I think the El Nino example is a good example of something that we thought we understood pretty well, and perhaps we don't understand as well as we once thought we did.
Awesome. Obviously, in this group, we have a ton of people who are really focused on actions, preparing for and mitigating climate change. And so there was just a question about what interventions are best to focus on. And this could be things like on the community level or on a bigger level.
I think the when it comes well in general, I think it is really important to think about the need for climate adaptation. We often hear in California about California being a leader in reducing greenhouse gas emissions or climate mitigation, so the things we need to do to mitigate the underlying problem of climate change. But I think sometimes lost in that is that we really do also need to be doing climate adaptation in the meantime. And the good news about adaptation as opposed to mitigation, the challenge with mitigation, of course, is that climate change is a global problem, and that as important as it is for California to be a leader globally in doing so, California cannot solve that problem on its own. It requires global action and global buy-in. Adaptation is different. Adaptation is something you can do effectively in some cases, especially when it comes to something like wildfire, for example, even at the level of an individual property owner or even a renter. We're renters, and we've talked to our landlords about the juniper bushes in the yard. So you can actually do things that are potentially uh, really effective at local scales and quickly when it comes to something like wildfire. So thinking about home hardening, the big conversation when it comes to wildfire risk, ember resistant vents, thinking about what vegetation is right up against residential structures in wildfire risk zones or not, thinking about those wooden fences or not. That's something that can protect your home immediately when you do it. You don't have to wait decades, you don't have to wait for the government to come and do it. That's something you can do yourself. Also, there's local, community, state level kind of actions that can be similarly effective. Prescribed fire, thinking about community planning and evacuation planning for wildfires or other hazards that can become immediately relevant, immediately implemented in a way that doesn't require waiting for everyone else in the world to get their act together, that has immediate tangible benefits. And so I do emphasize a lot of those sort of bottom-up, grassroots, community to state level actions for some of these climate adaptation measures, not only because they're really immediately useful, but also because they make, we can do them even in an environment where perhaps the federal government is not being as helpful in moving that forward, or where there's less certainty where we may be headed next, that's still something that you, the individual, you as a member of your community, you as a member of a state that votes on things can potentially accomplish.
Awesome. Awesome. So we're at 101 right now. So I'm just going to thank you again so much, Daniel. Um, are you continuing your office hours on YouTube?
Yes, absolutely. It's something, my most recent one was last week. I'll probably have another one this week. I don't have them, one way they're different from ordinary professorial office hours is they're not scheduled at the same time each week. So they're a little bit more ad hoc, but I do try and have one about once a week, and I usually announce it at least 24 hours in advance. So if you subscribe to the YouTube channel, you should, and you turn those notifications on, you should be notified. I also try and post on social media once I have a time slot nailed down. So if you are interested, there's a few ways to find out, and I'll probably have my next one talking about the monsoon surge and the mountain thunderstorms this week.
Awesome. Awesome. Thank you so much. Well, I know that we weren't able to get to all of our questions, but I want to respect everyone's time. Thank you so much for joining. And I hope that you have many more YouTube followers from this presentation. I know that so much of what you said was so interesting to me because I've heard a little bit about the water variability, and your explanations were so clear and made me feel more confident in my ability to talk about it with others. So thank you again. I'm just going to stop the recording.